Hello everyone, this is Raghav SMA of the Gate Academy. So in this video we will solve a question from Entropy, and it's a very interesting question, and this type of questions are frequently asked in Gate and engineering services. And if you look at the question is something like this. In an experimental setup, air flows between stations P and Q adiabatically. The direction of flow depends upon the pressure and temperature conditions maintained at P and Q. The conditions at station P are 150 kilopascal and 350 Kelvin, and the temperature at station Q is 300 Kelvin. The following are the properties and relations pertaining to air. Specific heat at constant pressure Cp is 1.005 kilojoules per kg Kelvin. Specific heat at constant volume is Cv 0.718 kilojoules per kg Kelvin. Characteristic gas constant are 0.287 kilojoules per kg Kelvin. Enthalpy H for air is written as Cp times T, and internal energy for air U is written as Cv times T. Specific enthalpy and specific internal energy. And the question is, if the air has to flow from station P to station Q, the maximum possible value of pressure in kilopascal at station Q is close to. He is saying that if the air has to flow from station P to station Q, what should be the maximum value of pressure at station Q? So the conditions at station P and Q are given. So they are like this. So I am assuming it's some kind of duct. So this I am assuming it's station P, and this I am assuming it's station Q. He is saying that air has to flow from station P to station Q. The conditions at station P are given. It is 150 kilopascal and 350 Kelvin. So here the pressure is 150 kilopascal and the temperature is 350 Kelvin. And at station Q, so only temperature is given, so pressure is not given. Temperature is given as 300 Kelvin. Temperature here is 300 Kelvin, and we don't know the pressure, and the question asked here is, for what value of maximum pressure at station Q, air will flow from P to Q. And he is saying that, so the flow process is occurring in an adiabatic manner. It means that there is no heat transfer, so from the gas to the surroundings. I am assuming this duct is completely insulated. And how to solve these kind of questions? How to solve these kind of questions? It's very simple. He is saying that air has to flow from station P to station Q. If air is flowing from station P to station Q, it means that some process has happened in the universe. And we all know that, so from entropy principle, only those processes will happen in the universe for which change in entropy of the universe is either positive or zero. If change in entropy of the universe is positive, it means greater than zero. It means that some irreversible process has occurred in the universe. If change in entropy of the universe turns out to be zero, it means some reversible process has happened in the universe. So there are only two types of process, one a reversible process and second one is an irreversible process. So I can say like this, only those processes will occur in the universe for which change in entropy of the universe is either greater than or equal to zero. If change in entropy of the universe comes out to be less than zero, so which is not possible, which is against entropy principle, that kind of processes will not happen. Only those processes will occur in the universe which tend to increase entropy of the universe. Okay. So in the question he is saying that air has to flow from station P to station Q. I am assuming this is station 1 and this is station 2. Since it has to flow from station P to station Q, so and I told you that so change in entropy of the universe must be greater than or equal to zero for a process to occur. Change in entropy of the universe is nothing but change in entropy of system plus change in entropy of surroundings. This must be greater than zero. So here if you assume something as system, so the other interacting body will become surroundings. Now see here, I am assuming this gas that is flowing through this duct is my system. So if I assume this is my system and this is my surroundings, and you can see here, so there is no heat interaction between the system and surroundings. Since there is no heat transfer between system and surroundings, so there won't be any change in entropy of surroundings. I can say like this. So change in entropy of the universe is the same as change in entropy of the system. Here in this case, this must be greater than 0. And it's an ideal gas flowing from one state to another state. So change in entropy of an ideal gas when pressure and temperatures are given, we can write like this. So this is Cp into log T2 by T1 minus R log P2 by P1. This must be greater than or equal to 0. Or I can write like this. Cp log, so T2 by T1 must be greater than or equal to, so R log P2 by P1. So the value of Cp and Cv are given in the question. Cp is given as 1.005 log T2 by T1. So T2 is 300 Kelvin and T1 is 350 Kelvin. This must be greater than or equals to, R is 0.287 into log, so P2 by P1. So pressure at state 2 is not known, but pressure at state 1 is given as 150 kilopascal. So if you simplify this, you will get, so pressure at state 2 must be less than or equal to, it's less than or equals to 87.43 kilopascal. I can say like this, so pressure at state 2 must be less than 87.43 kilopascal, or the maximum case, so it must be at least equal to 87.43 kilopascal. If the pressure at state 2 is more than 87 or 87.43 kilopascal, then air will not flow from station P to station Q. The maximum value of pressure, so for which air flows from station P to station Q, is 87.43 kilopascal. If the pressure is slightly higher than this, air will not flow from station P to station Q. If the pressure is slightly less than this, so then it's obvious that the air flows from station P to station Q. For all values of P2 less than or equal to 87.43, air flows from station P to station Q. So whenever some kind of questions are given like this, so we have to assume this condition. So change in entropy of the universe must be greater than or equal to 0. Only those processes will occur in the universe. Thank you.